Okay, good afternoon, boys and girls. Today's lesson, I'm going to go through with you guys on metals and extraction of metals. Very disappointing. I just found out that not many of you actually go into LMS and actually downloaded the the notes on acids, on bonding and solid liquid gases, and even lesser of you actually, wouldn't say less than 10% of you actually even bothered to download the acids, bases and salts notes. Okay, so please do that. Download them, view them, copy them down on your textbook, okay, whatever notes that is flashed on the slides, and then after that view the videos, okay, especially for this coming Wednesday when you will have a test on both acids, bases and salts as well as metals. Okay, it's very, very important for you to do that. Please discipline yourself. Okay, as I was saying at the Facebook shout out, if I don't see 60 views on any of the slides on those three slides, okay, so I will not bother to upload any more slides on the coming weekend. Alright, because I think some of y'all don't bother, so I think myself don't need to waste my time. Okay, so these notes, this next topic has something to do with metals. Metals are usually very frequent topic that will always come up for O levels. Okay, so before we really dive into the more important components of metals, let's look at the physical properties of metals. A lot of you can able to identify what are the physical properties of metals. Basically, the physical properties of metals are they have high densities, they have very high melting point, and they have high boiling point. Okay, so before we talk about why do they have these properties, we have to look at the particulate model of many metals. Okay, basically when you talk about metals, okay, we're talking about atoms, and some of y'all at your bonding tests. Okay, some of you, when we talk about copper, remember copper metal, I asked you all what happens at solid copper and what happens at liquid copper. A lot of you all talk about molecules. Okay, please take note, molecules is not present in metals. Okay, when you talk about metals, you're talking about atoms, and the atoms in metals are packed tightly in layers and are held together by strong metallic bonds. And we thought about these metallic bonds is the same as your electrostatic forces of attraction. Remember that? Okay, electrostatic force of attraction is also available at ionic compounds. Okay, so besides ionic compounds, it's also prevalent in metallic bonding. Okay, so because a lot of metals, they are in solid form, there's only one metal at room temperature that is not solid, that is mercury. Okay, so virtually all metals are solid. Okay, so they are packed tightly in layers, regular arrangement, vibrating about in fixed position, okay, and held together by strong electrostatic forces of attraction. Okay, so because of the structure itself, right, when let's say when you ask yourself why is it ductile and malleable, in prelim 1 a lot of you all talk about ductile and malleable as separate physical component. Actually they are the same, they are one and the same physical component. So if they are ductile, it's also known that they are malleable as well. In pure metals, atoms of the same size, okay, if they are same size, okay, they are packed regularly in layers. So basically it is very easy for the layers of atoms to slide over each other when you exert a force on any side. Okay, just like the diagram showed. Okay, so as long as you give me the keywords there, okay, I will usually accept the mark. This question, they always like to ask, and they always like to give about 2 marks. Okay, so if you give these two factors, these 2 points obviously you will earn them. Okay, so always remember your arrangement and the size of the atom is almost the same. Arrangement is they are packed regularly in layers, and because of that, if you exert a force on any one side, okay, the layers of atoms can easily slide over one another. Okay, that's why it's ductile malleable. Now, another common question that they like to ask is, why do metals conduct electricity? Okay, now if you look at this slide here, okay, basically your metals, remember metals will always give away electrons or lose electrons, right? So when they give away electrons, where do the electrons go to? Now in ionic bonding, the electrons will easily go to a non-metal, okay? But for metals, for metallic bonding, the electrons don't go anywhere. So basically, they'll be here. Okay, they'll be here, they'll be here, they'll be here. We're basically where all the blue spots are. Okay, they're just swimming around. Okay, so if you are asking yourself, cannot be why? Basically, how can electrostatic force of attraction happen in this case when we have plus all together? Remember again, electrostatic forces of attraction will only occur if there's plus and minus together. Okay, so in this case, your negative, your electrons are all around. Okay, you see all these positive charge ions here. Okay, they are bonded together. So your free moving electrons basically act as a glue. Okay, as a glue all around your cations. Okay, so basically it is the glue that hold all the cations together. They're just swimming around. Okay, so because they are around there, your mobile electrons actually allow the metals to conduct electricity. Okay, so from here I want to give another misconception. A lot of y'all just said in the previous bonding test, oh, why do ionic compounds conduct electricity? Because of mobile electrons. Okay, that's not quite true. The one that gives that can conduct electricity because of mobile electrons is metals. Okay, because of this factor. Okay, so please remember this part. Okay, you have your arrangement of metals where it's a positive metal ion surrounded by a sea of free moving, or another word you can call it is delocalized electrons. Okay, that's why because of the presence of the delocalized electrons, then you can conduct electricity. Okay, now basically how you explain whether the metals can conduct heat is the same reasoning also. Okay, your metals actually, okay, let's go on to the next slide. Okay, your metals in because of your sea of free moving electrons. Okay, so basically your electrons act as charge carriers. Sorry, if conducting electricity, it acts as charge carriers. For conducting heat, it acts as heat carriers. Okay, so it carries heat from one end to the other. That's why your metals can conduct heat very easily. So when they conduct electricity, they will carry the charges from one end to the other. So same thing. Okay, so without this sea of free moving electrons, they are not able to conduct heat. They are not able to conduct electricity. But because they have, then they can do so. Alright, that's quite fast. Now basically, essentially all the stuff that you see around you, okay, when they are made out of metals, they are not pure metals. And the reason why pure metals are not widely used is because the truth is many pure metals are soft. Okay, they are not as hard as you think. And the second more important reason is many of these pure metals, they will react with either air and water, and so they will corrode easily. So when you talk about whether they can react easily with air and water, you're talking about corrosion. Okay, later on we'll talk about rusting, and rusting is actually a form of corrosion. Alright, now so mankind know that pure metals is not reliable, cannot be trusted. So we developed this idea of alloys. Now alloys are actually a mixture of metal with one or few other elements. Okay, so for example, if you look at bronze, now usually third placing people involved in races or any sort of sporting competition, they'll be awarded bronze. Okay, and usually bronze is actually brown in color. Okay, it looks like a poorer cousin of gold. Okay, How do you develop bronze itself? Bronze is an alloy of copper and tin. Okay. Another alloy that you probably know of, especially for those in bands and concert bands, Chinese orchestra, is brass. Brass is usually used for musical instruments. Okay, trumpet is made of brass, tuba and stuff like that, and it's an alloy of copper and zinc. Okay, and the most frequently used alloy of them all is stainless steel. Okay, you use the back of your watches, your window grills sometimes. Actually stainless steel is an alloy of iron, chromium, nickel and carbon. Okay, now I want to bring you to the fact that if you look at your textbook, a lot of them actually they say that an alloy is a mixture of copper and a mixture of metals. Okay, that is not quite true. Okay, why is it that it cannot be a mixture of metals? Actually, if you look at stainless steel has iron, chromium, nickel and carbon is not a metal. So inside your textbook, please try to correct that misconception. If there's a definition question in your exam and you write alloy is a mixture of metals, I cannot award you your mark. Okay, so this is the true definition of what an alloy is. It's a mixture of metal with one or few other elements. So when you talk about one or few other elements, then basically you've covered whether the element is not specific lah. It's not specific as to metal or non-metal. Okay. Alright. Now, why are metals often used in the form of alloys? Okay, reason number one, to counteract reason number one that why pure metals are not used, easily alloys are stronger and harder than pure metals. Now let's look at why alloys are stronger and harder. Okay, now remember alloys is basically two or more, it's like a mixture. Actually it is a mixture, it's not like a mixture, it's a mixture already, where you have two or more elements inside. Okay, not chemically combined together. So when a pure metal is alloyed, a different element is added. So in this case, just now you see all the blue balls, all blue balls regularly arranged, right? So in this case, you have one green ball there. It represents a different size element. Okay, so when you add a different element to it, okay, what happens is now you have different sizes and the arrangement is no longer regular, no longer nicely propped up. Okay, and when you actually exert a force, okay, from any side, you realize that now the regular arrangement of atoms is already broken up. Okay, and when it's already broken up, okay, it gets harder to actually slide, okay, any one side. If you exert any force from the top, from the side, from the bottom, it's actually quite hard to slide over. Okay, in comparison to you have all the blue balls regularly arranged together. Okay, so because of that, okay, alloys are easily stronger than pure metal. So if you have stainless steel, you have 4 different types of elements all inside. Can you imagine? All the arrangement is all jumbled up together. Okay, so the keywords that you need to look out here is breaks up regularly arrangement of atoms, and the atoms of different sizes cannot slide over each other. Okay. Alright, let's proceed. This question is really easily asked for many tests and exams. So please study hard. Study the keywords by heart. Okay. Now, why are metals often used in the form of alloys? Reason number 2. Okay, this one is for a very superficial reason. It can be used to improve the appearance of the metal. So, for example, if you look at bronze is copper and tin. Okay, you could probably argue, hey, Mr. Gad, is just, bronze and copper, the color is virtually the same. So you just use copper. Okay, but copper is very soft. Bronze, on the other hand, you bite also until your teeth is gone, also you cannot bite through it. Okay, so basically it has the same appearance. Okay, but you compare, when you alloy it, you retain the attractive appearance of certain metals, but you get other qualities as well. Alright, so in this case, the appearance is off. So let's say it uses the example of pewter. A lot of you do not know what's pewter. Last time old people, they like to your grandparents generation, they like to collect ornaments such as teacups, all those that are made of metals, saucer, plates, stuff like that. And these things are actually made out of pewter. Okay, pewter, you compare it to the appearance of tin. Tin is very dull. Okay, it looks like those cans, can of sardine that you buy. You unwrap the whole thing. It looks very dull. But when you convert tin, you mix it up with antimony and copper. Okay, you don't need to know what's antimony. It's a form of other element. Actually, the pewter looks more striking. Okay, and it straight away becomes more attractive. And when you make all these ornaments with pewter, then it actually attracts consumers to buy it. Okay, now reason number 3, okay, a much more important reason to combat why pure metals are not used. Alloys are actually more resistant to corrosion. Now let's say pure copper. Okay, pure copper corrodes easily. Now later on you will learn that actually pure copper is unreactive, but still over time it will corrode. Okay, but when you actually use an alloy of copper, you mix it up with something else, it is used to make coins. Okay, so last time the 1 cent coins is actually made out of copper. Reason number 4, okay, alloying is also used to lower the melting points of metals. Let's say soldering. Soldering is an alloy of tin and lead. Okay, so usually like when you want to open up your handphone parts, you go to all those abeng shop, they always make use of soldering. And when they solder something, all the small little parts, because they want to actually fuse certain things, they actually make use of solder to lower the melting point so that it will melt. Okay, now these are some of the common alloys. Brass, of course, is copper and zinc. Does not corrode easily, look like gold, and usually are made out of coins and musical instrument. Stainless steel, resistant to corrosion, very strong. Usually you use it to make cutlery utensils. Solder, usually you lower the melting point for joining metals. And lastly, pewter. We already talked about decorative ornaments. Looks bright, shiny, looks like silver. Okay, so see, these are all the common alloys that you will see. Okay, so that's the first part of our notes that we've already covered. Okay, hold on. Let's go through the second part. Okay, the second part basically covers your chemical reactions, okay, of your metals. Now, chemical properties of metals, I'm sure all of you will have known by now, because basically this is a revision topic. And number 1, it forms positive ions by the loss of electrons. Okay, so usually how do you identify metal? How do you define metals? A lot of you have been asking me, Mr. Gan, how do you identify metal? Metal is a metal lah, and I always say, you want to answer that question, basically you define it by loss of electrons. Only metals lose electron. Then non-metals non-metals will gain electrons. So that's how you differentiate between metals and non-metals. Some of you are very cute. You all tell me, oh, how do you want to know whether it's metals or not? Look at the periodic table, look on the left hand side. Okay, that one is actually for yourself. Okay, for you to basically find out where are the metals, to look out metals in the periodic table, you look on the left hand side of the periodic table. But if you have to give an answer to examiners, you cannot tell them that. Okay, so how do you answer that kind of question? By losing electrons. You can lose either 1, 2 or 3 electrons, and they will form positive charge ions. Reason number 2, okay, they will form ionic compounds. Okay, they can form metal chlorides, metal oxides, metal sulfides, so on and so forth. Okay, reason number 3, they usually react with dilute acids to give hydrogen gas and salt. This one by now you should be able to master it. Remember it by memory already. Okay, and reason number 4, they will react with oxygens to either form basic oxides, because they are metal, right? Remember, metal oxides are basic oxides, or amphoteric oxides. If you can recall, amphoteric oxides got how many? Okay, got 3. Okay, lead 2, aluminium and zinc. Okay, let's forget about that part. Okay, now let's proceed. Now, metal may react more or less vigorously with a substance than another metal. Okay, so usually last time, how do scientists basically compare which metal is more vigorous? Basically, they just add lah. Okay, so in this topic, we'll actually uncover certain things, how a metal reacts more vigorously than the other. Then we table it into a reactivity series. Now, first up, we compare it with cold water. Some metals react with cold water to form metal hydroxide and hydrogen gas. Okay, so which metals will react with metal hydroxide and hydrogen gas? Later we cover. Okay, basically your first four metals. Okay, so in this case, your potassium, sodium, calcium, and magnesium, okay, will react with cold water, H2O, to give hydroxide and hydrogen gas. Okay, so always remember potassium, sodium, calcium, and magnesium. Okay, the slowest is of course magnesium lah. Magnesium will react after a few days only. Okay, then you will give off a hydrogen gas for a few days. The most violent one, potassium. Some of you have asked, Mr. Gad, how come only potassium, sodium, calcium, and magnesium? Then how about the rest of the group 1? Of course, if you learn your periodic table properly, you realize that potassium is not your strongest group 1 metal, right? So obviously when you compare it with cesium or francium, the stronger group 1 metals, they will react even more violently, even more explosively. But when you talk about reactivity series, you are only comparing with all these metals only. Okay, so you realize that your reactivity series don't have cesium, don't have francium, don't have lithium, so on and so forth. We just have to simplify it. But you know, when you want to make relations that way, you have to infer for yourself. Okay, so how about the rest? Zinc, iron, lead, copper, silver, gold, they all do not have any reaction. Okay, so when you dump them in cold water, nothing happens. No bubbles, no nothing, you know, nothing lah. Okay. Okay, let's proceed. Okay, so always remember they will give hydroxide and hydrogen gas. So the bubbling you see, if you test it with lighted spin, then you'll get the lighted spin will extinguish with a pop sound. Okay. Now, which metals only react with steam? Okay, now when they do react with steam, okay, like for example zinc and iron, they do not react with cold water at all, but they do react with steam, and when they do react with steam, they will give metal oxide and hydrogen gas. So there's a difference between cold water and steam. Okay, so let's see, like for example magnesium, zinc, and iron. Okay, when they do react, okay, they will give these things: oxide and hydrogen gas. Okay, now please take note, magnesium is the only one can react with cold water and steam. Okay, so if you can recall, when they can react with cold water, it will give hydroxide and hydrogen gas. When it reacts with steam, it will give oxide and hydrogen gas. That is the only difference. Okay, the rest all you should be able to distinguish. So for zinc and iron, they do not react with cold water, no problem there. But when you give them steam, they can still react. Okay, for zinc, it will give you zinc oxide and hydrogen gas. For iron, they give you iron oxide and hydrogen gas. Of course, iron is the slowest out of all that. Then some of you all ask, Mr. Gad, then how about sodium, potassium, calcium? Never mention anything. Okay, basically sodium, potassium, and calcium, okay, when they react with steam, okay, they will give you, again, same thing hydroxide and hydrogen gas. Okay, they won't give oxide or hydrogen gas. Okay, why? Because the reaction is too vigorous. Okay, so that's why they said, do note that the metals such as potassium do react with steam, but it's the same reaction as water. Now basically you compare steam and water, they are actually the same thing, same formula. but obviously steam is easier to react with than cold water. Okay. Now last one is metal plus dilute hydrochloric acid. Okay, now metal plus dilute hydrochloric acid, you will get metal chloride and hydrogen gas. Now some of you ask, then Mr. Guy, how about metal plus nitric acid? Metal plus nitric acid, then it will give you metal nitrate and hydrogen gas. Simple as that. Okay, then what if it reacts with sulfuric acid? Then if it reacts with sulfuric acid, what will it give you? It will give you metal sulfate and hydrogen gas. Okay, so you can see lah, basically some of your, and I see that you don't know how to name the salts. Very sad. Okay, please chain up. Hydrochloric acid will give you chloride, nitric acid will give you nitrate, sulfuric acid will give you sulfate. Okay, stuff like that. Alright, so let's proceed. Okay, now let's say about sodium and potassium. The top two give you a very explosive reaction. Okay, it's not supposed to carry out in the lab. Calcium, magnesium, zinc, iron. Okay, they will react. Of course, calcium being the more violent one, and iron being the more slower one. Some of textbook says that lead also does react, but it will take a lot of time. Okay, so basically, if you look at it, sodium, potassium is the fastest. Iron is the slowest. Lead, copper, silver, gold, they are totally useless. Cannot react at all. Right? So don't think you want to basically destroy your mother's gold ring or something. You just put in acid. You put it in acid also no use. Okay. So from there, the scientists are able to deduce what is your reactivity series. Okay, and your reactivity series in the O-level syllabus are only made out of these metals. Okay, of course, plus gold lah. Okay, you have your most reactive, your okay, your most reactive being your potassium. Okay, and then followed by your sodium, calcium, magnesium, aluminum, zinc, iron, lead, copper, silver, and lastly gold. Some of you are asking me, Mr. Guard, do we need to memorize the reactivity series of the metals? Yes. After a while, you quite get used to it lah. Obviously, in exams, they won't ask you to compare between magnesium and aluminum. Okay, but some of the harder prelim questions, they would ask you to do so. Okay, so it'd be good if you can memorize the order. Okay, if you can't, then it's okay. Alright, like for me, I've never memorized, but after a while, when you get used to it, okay, then you soon get it lah. Okay, so that's it for metals. Okay, we can now proceed on with extraction of metals. Okay, I think extraction of metals, I'll probably move on to the next video, or else it could probably be quite draggy. Okay, so stay tuned for the next video, and then after that, that's it. So please look through the video again. Before you look through this video, remember, copy down all your notes. Okay, look through the video, then you can do your things, please. Okay, see you all later. Bye bye.